Hi everybody, and welcome to my ESA recorded talk. So I will talk about a approximation algorithm for the K-connected M-dominating set problem. So we will start with a few definitions. So a subset S of nodes in a graph is said to be a K-connected set if it induces a K-connected graph. And it is called an M-dominating set if every node not in S has at least M neighbors in S. And we will say that a subset S is a K-connected M-dominating set, or KMCDS for short, if it is both K-connected and M-dominating. So here you have an example of a two-connected set, the yellow nodes. The subgraph induced by these nodes is two connected, but this set of nodes is not even dominating. When I say dominating, I mean one dominating. There is a vertex in the graph that has no yellow node as a neighbor. This is the right upper vertex. It has no neighbor it has no yellow neighbor. So this is a two connected set, but it is not a dominating set. However, if we choose three other vertices, we can get a two connected dominating set. So these three vertices induce a cycle in the graph, so it's a two connected graph. And every wide vertex, every vertex not in the set, has a yellow neighbor. So this is a two connected set and a dominating set. Moreover, you can check that in fact this set is also two dominating, since every white node has a yellow neighbor. So this is a two connected, two dominating set, or 2-2 CDS for short. If we want to increase the domination, say if we want a two connected, three dominating set, then actually we will need more vertices. So if we choose these four yellow vertices, then they will form a two connected, three dominating set. They induce a two connected graph, a cycle, and moreover, every wide vertex has at least three yellow neighbors. So this is a two connected, three dominating set. So in the problem, we will consider the K-connected M-dominating set problem, or KMCDS for short. We are given a graph with node weights and integers K and M. And they want to find a minimum width K-connected M-dominating set, a subset of vertices that induces a K-connected graph and dominate, and every vertex outside S has at least M neighbors in S. A motivation for this problem is actually quite obvious, is constructing a cheap, fault-tolerant virtual backbone network. So here you have a solution. It has four vertices. We actually saw it before. This is a solution for the values K equals 2 and M equals 3. So this is a two connected, three dominating set. And the value of this solution is 12, because the vertices have weights. And if we summate the weights of the vertices in this set, then it will be 12. So what do we know about this problem? So let's start with small values of M and K. So the case K equals 0, when we actually require no domination at all, no connectivity at all, but only certain amount of domination, is actually the set multi-cover problem. And this problem admits a tight ratio all on n in general graphs, and also order 1 in uni-disk graphs. So I'll discuss here both general graphs and uni-disk graphs. The case when K equals M equals 1 is called the connected dominating set problem. And it also admits a tight ratio O1n in general graphs and order 1 in unidisc graphs. And this ratio, the ratio O1n, is actually achieved by a reduction to the node-weighted Steiner tree problem. So the connected dominating set and the node-weighted Steiner tree problem are almost the same. If we consider the case when k is larger than m, then actually we have only one non-trivial approximation algorithm, and it achieves ratio roughly or order of ln to the 4th n. And this problem is related to a slightly more complicated problem called subset Steiner connected dominating set, which is in turn related to the group Steiner tree problem. But we have only one algorithm for the case when k is larger than m. What happens when m is larger than k? Then we have a fairly good ratios. We have a ratio OK squared ln n in general graphs, and we have a ratio order k ln k in unidisc graphs. So the ratio in general graphs, so for any constant k, it's actually just ln n, which kind of matches the cases that the case that we already know, k equals 1. Also the best ratio is ln n. And in unidisc graphs, for any constant k, we have a constant ratio, which is also quite good. And in both cases, the problem we consider is related to a problem called subset k connectivity, which I'll describe right now. But before that, I would like to tell you what is the improvement that I achieved. So in general graphs, I reduced the ratio OK squared ln n to order k ln n. And this is an improvement by a factor of k. And in unidisc graphs, I reduced the ratio from or k ln n to a certain expression given here. And let me explain you what is this expression. So essentially, if you look at the term in the brackets, when m is a bit larger than k, when k is not too close to m, then the expression written in the brackets is actually a constant. So say m, when m equals 2k, then m over m minus k plus 1 is a constant. So we get a logarithmic ratio instead of linear ratio. So a significant improvement. On the other hand, if m is very close to k, the expression in the brackets is at most k to the power of 2 over 3. So it still improves the previous ratio k ln k, because we get a sublinear ratio, which is k to the power of 2 over 3 times ln squared k. So the improvement is roughly always to a sublinear ratio, the first sublinear ratio. And in addition, when m is not too close to k, we get a log square ratio. Okay, so let's see how this is done. So for this, I need to describe the subset k connectivity problem. So in this problem, the subset k connectivity problem, we are given a graph, a set of terminals. We also have node weights on non-terminals, and we have an integer k. The goal is to find the minimum weight subset of non-terminals, such that the graph induced by the terminals and the chosen set of non-terminals contains k node disjoint ST path for every pair ST of terminals. So in the induced subgraph, we require k connectivity only between the terminals. So we have terminals, we want to add additional nodes such that there will be k node disjoint path, node internally disjoint path between every two terminals. So we require connectivity between the terminals, but no connectivity is required between the non-terminals. So for example, in this example, if our terminal set are the yellow nodes, and k equals 2, then by adding the node of weight 2, we obtain a feasible solution. Well, in this case, actually get a two-connected graph, but this is not required. We just need to get two disjoint paths between every two terminals. So what is known for this problem, and later I discuss how it is related to the KM to KM CDS problem, to the KM CDS problem. So the subset K connectivity problems admits the following ratio. We have ratio K squared ln N in general graphs. And also we have ratio K squared ln K in unidisc graphs. So let's see how our problems are related, how subset K connectivity and the K connected M dominating set are related. So let us denote by alpha the best known ratio for M dominating set. And it should be noted that alpha is fairly low compared to the ratio to the KM-CDS. So alpha equals log n in order of log n in general graphs and order 1 in unidisc graphs. And beta is the best known ratios for subset K connectivity, with the additional requirement that the instances are special. When I say instances are special, this means that T is already a K dominating set in the graph. So beta denotes the best ratio for subset K connectivity, such that the set K of the set T of terminals is a K dominating set. So the first lemma, the first lemma that is needed, that we'll need, is that the KM-CDS with M greater or equal than K admits ratio alpha plus beta. So I will prove to you this lemma, or at least sketch the proof. And the second thing that is needed is that actually abounds on beta. So approximation algorithm for subset K connectivity when T is already a K dominating set. So essentially a proof for the bounds I beta that I prove are essentially coincide with the ratios I stated for the KM-CDS problem. So let's see. So if you combine these two results, you see alpha is much lower compared to beta. So essentially the dominating ratio here is beta. And on the beta, I prove the bounds that are needed. So from these two, you get the result. So okay, let's see that we can prove the lemma, or at least sketch the proof. So the lemma says that KM-CDS with M greater or equal than K admits ratio alpha plus beta. And the proof is quite simple. We apply the following algorithm. We compute an alpha approximate M dominating set, and we denote this computed set by T. And with this T obtained at step 1, we find the beta approximate subset K connectivity solution. So first thing to observe is that the union of T and S is a feasible solution, and I will not prove it. You can find the proof in the paper. Actually, you cannot find the proof in the paper. You can find references, at least 3 references to papers where it is proved. But it is a known fact. I will not prove it. I'll just sketch you, but I'll sketch you why this is an alpha plus beta approximation ratio. So let us denote by a star an optimal solution for KM-CDS. Okay, Now, the point is that the union of T and S star is also a feasible solution. Why? So here we use another known fact that if we take a K-connected graph and connect and take a new node T and connect it to at least K vertices in this graph, then we again obtain a K-connected graph. So adding a new vertices and connecting it to K nodes of a K-connected graph results in a K-connected graph. So it means that if we take a S star, which induces a K-connected graph, we take this induced K-connected graph, and that's add the nodes in T one by one, then this node, since S star is an M dominating set, and M is at least K, then adding this one vertex of T to S star, to G, to the subgraph induced by star, gives again a K-connected graph. And if we add another vertex, we get a K-connected graph again, and so on. So T union S star is also a feasible solution. And now, but now see what happens. S is a beta approximate solution. So the weight of S is at most beta times the weight of S star. S star is some optimal solution. S is a beta approximate solution. So the weight of S is at most beta times of S star. And clearly the weight of T, the M dominating set solution, alpha approximate M dominating set solution, is at most alpha time the weight of S star. So if we take the union, then it's alpha plus beta times the weight of S star. So the approximation ratio is alpha plus beta. Okay, so assuming we proved this lemma, now just what we need to do is to prove certain bounds on beta, namely that the subset K connectivity problem such that T is a K dominating set admits certain ratios OK lambda N in general graphs and some expression times the order lambda square K in unit-disk graphs. So let's start with it. And I composed the special proof for you. It's very short actually. And here it is. Yeah, it's a complicated proof. I cannot describe it here. I need at least something like 1-2 hours. So, but you can find it in the paper. So that's it. Essentially, I described the way I solved the problem. Okay, so let's summarize. So we have a certain, this paper analyzes the K-connected M dominating set problems for the case when M is at least K. And the improvement for general graphs is by factor order K from K squared ln N to K ln N, order of. And for unit-disk graphs, the previous ratio was order K ln K, and it is improved. So this is essentially a superlinear ratio. K ln K is a superlinear ratio. It is improved to a logarithmic ratio in the case when M is larger than K, when K is not too close to M. But in the worst case, even if K is close to M, the ratio is still sublinear, at most K to the power of 2/3. I would say a natural questions is whether we can get a constant ratio for unit-disk graphs. There is no, for any K, there is no evidence so far that this is not possible. Another open question is, can we obtain some good ratios for the case when M is smaller than K? As I told you, there is actually one such result, and it is for the case M equals 1 and K equals 2. That's it. So thank you for listening for the talk, and hope next time we will meet face to face after the coronavirus is over. Thanks. If you have any questions, I'll be glad to answer.